Dr. Pawinder Kaur.
Thank you, Acting President. I would like to begin by acknowledging the excellent motion by the Honorable Klasey Hirst and all the speakers we've heard this morning. It's a really good conversation to have. My first interaction happened with a rare disease in 2018 when I was working as one of the pioneers in terms of bringing the technologies together to read the DNA. Because as you all know, 1 in 2,000 people are affected by the rare diseases, and 80% of them are actually genetic diseases. So when I was working as a geneticist, this was one of the very important things to be able to diagnose these rare diseases. You need to be able to read the DNA of a person uninterrupted without much errors. And that has been a field of science in itself. 2001, we've had the very first adventure into putting the entire DNA of a human together. 2009, when after a decade we achieved that, it costed $2.7 billion to put the very first human DNA map together. But it also took a decade, but still there were a lot of gaps in that, which has been filled over the years. And only 2 years back when we had a telomere to telomere DNA sequence of a human. You talk about human and why it is so difficult to diagnose these diseases. Each one of you, or every human on this planet, has about 37 trillion cells in their body, and each and every single cell of that in your body has a DNA, which is approximately 3 billion letters. They're 4 letters only, and they rearrange themselves, A, T, G, C, and we happen to actually have the 4 letters DNA colors right here. Honorable Katrina Stratton, who is wearing blue today, has left the chamber for urgent parliamentary business, but between me, Klasey, the Honorable Iyer, and Honorable Katrina Stratton, we had all the 4 letters colors. So what happens is these 3 billion letters, which is A, T, G, C, really repeating themselves, even if a single letter, and these 3 billion letters are coding for 20,000 genes, which makes us who we are, how we function, how we expose to different diseases, how we react to different situations that we come across. So these 4 letters arrange themselves, code for the 20,000 genes in your body, and even if there is a single letter which does not get correctly placed in your 3 billion sequence, you end up with a condition, because that could happen to be in a gene which is coding for a very important function in your body. So that is how the rare diseases happen, and that is what we need to be able to diagnose these diseases. And if you just do your math, 37 trillion cells in every human, 20,000 genes it's coding for, you get the complexity that why it has been such a difficult task to be able to do. But I'm standing here today because there is a lot of hope, and I wanted to share all of that with you guys, with all of you honorable members, because it is not a life sentence anymore, because there is a really amazing advancement that has happened in the field of science and technology in the past few years. As I said, the first DNA map was put together in 2009, and after that, 2012 was a major year in the field of biotechnology or science when the CRISPR technology came into effect, for which Emmanuel Charpentier and Professor Jennifer Doudna actually won the 2020 Nobel Prize for Chemistry as well. And that has been a breakthrough, because what CRISPR does is it is a very precise way of editing the DNA of any living form on this planet. And it is so precise that it can actually go and identify that single letter that has been mutated in your body, which is causing the disease or causing the condition that you have, and this can go and attach to that particular letter, disrupt that gene, and not just identify it, but also go and replace that with the right functioning letter. All of this has happened, and there is a lot of economic challenges to be able to bring those cures to the people. And I want to share my interaction that actually shaped my career in biotechnology later on, which happened in 2018 when I was I was helping the Kids Research Institute here to set up their first personalized medicine center. We were looking at different ways to read the DNA, and I happened to be provided a DNA sequence which was for a 7-year-old child who's been going through a rare condition, undiagnosed, and I happened to put that DNA together as a three-dimensional sort of the whole information which led to the diagnosis of that 7-year-old child. And I still remember the day when I was sitting next to the clinician with the parents and the child, when the clinician actually explained to the family what is wrong with their child. These parents have been waiting since the child was born for 7 years for a diagnosis, just to know what is wrong in there. That was a very emotional moment for me, not as a researcher, but as a mother of a 5-year-old at that point of time. And that was the day. I could not continue doing that as a profession. I really enjoyed my plants and animals because I didn't have to go through that emotional. It was quite hard for me. I came back to UWA full time after that and focused on my plants and animals and founded DNA Zoo. But that definitely strengthened my commitment to do the open source science and not put this information behind the paywalls, because it is very, very important for this really critical advancement in science to be accessible to all and being equitable to each and everyone in this society. And that's how we led all the discoveries in the DNA space after that and made it open source, equally accessible to everyone without any paywalls. Coming back to the good side of the story, as I mentioned CRISPR, and this is a real case which has happened last year. The very first personalized gene editing therapy was done in a 10-month-old boy, which was done by the University of Pennsylvania and Children's Hospital, Philadelphia. The boy was born with a CPS1 deficiency, which causes liver cell mutations, and it's a deadly and a fatal condition, happens 1 in 1.3 million children. So it's a very, very rare condition, and it needed a personalized solution for that particular child because the letter A was mutated, which needed to be actually letter G. And that's when the CRISPR technology was used. The child's actually doing really, really well. This happened last year. This was the very first person on the planet to receive a personalized gene editing therapy. So all I want to say is, there are a lot of examples now out there which are happening, and I would like to give a huge shout out to the FARI fund that we've set up here in Western Australia. A huge shout out to Minister Stephen Dawson, the leader of the House, because this fund has actually enabled this kind of research in our state, and we are kicking way above our weight, not just in Western Australia, but actually around the globe. And we have got the best longitudinal study data. We've got some of those data sets which not just going to help people of Western Australia, but they're going to be helping the people around the globe who are struggling with diseases like this one. So for families living with rare diseases, hope is no longer abstract. The help is available. It is not a life sentence. And hopefully we will be very soon seeing these technologies, not just reading the code of life, but actually rewriting that code of life and help with the conditions that many families suffer. And hopefully the future is going to be much better and brighter. Thank you so much.
Members